Hello and welcome to the another program of network analysis. Up to this point our analysis was limited for the DC circuits. Now we begin the AC circuit analysis. The DC circuit techniques that we have studied earlier can be applied directly to the AC circuits by using the phasors. So, in this program we will see how the nodal analysis, mesh analysis and theorems such as Thevenin, Norton and superposition can be used or applied in analyzing the AC circuits. Since these techniques were already introduced in the DC circuits, here our major emphasis will be to illustrate them with the examples. So, now we begin the analysis of circuit in which the source or voltage is time varying. Let us start with the Kirchhoff laws for the alternating circuit. We know the Kirchhoff voltage law can be written in the time domain as shown in equation. The time domain electrical quantities are represented by the small letters as they are varying with the time, but the phasor quantities can be represented by the boldface or capital letters as they are not varying with the time, they are representing only the amplitude and the phase. Thus, the Kirchhoff voltage law applies to the phasor voltage just as it did in the time dome. Similarly, we can see that Kirchhoff current law also holds good for the phasors, and by using this theorem we can write the Ohm's law for the AC analysis as V is equal to Iz, where Z is represent the impedance. Now, we have to follow certain steps to analyzing the AC circuit. First of all, we have to transform the circuit from the time domain to the phasor or the frequency domain. Then we have to solve that problem by using circuit techniques such as nodal, mesh, superposition theorem, as we want to use that technique in the phasor form, and then after getting the result in the phasor form, we have to again transform the result from phasor to the time domain. So, we start with the nodal analysis. As the KCL is valid for the phasors, so we can analyze the AC circuit by nodal analysis. The difference is that here in the circuit, instead of resistance, we have the impedances and which can be expressed as complex number. So, we have to calculate the complex values, but all other the treatment remain the same for the nodal analysis, and the sources will have amplitude and phase noted. We can understand this analysis by taking a simple example. In this example, we have to find the voltages V1 and V2, but first of all we have to transform this circuit from time domain to the frequency domain. So, we express the voltage source as the polar or phasor form, and then here in the circuit the inductance and capacitance values are given. Then we have to calculate the inductive and capacitive reactance by taking omega is equal to 2 radian per second. After getting all the values in the frequency form, now we have to simplify this circuit, as we have seen that there are some combination of reactances in parallel and series. So, we will simplify these combinations and then finally we get the circuit like shown in figure B. Now, we can calculate the phasor voltages V1 and V2 by writing the KCL equation for node V1 and V2. So, here we have write the KCL equation for node V1 and node V2, and we get the equation 1 and 2. Now, these equation can be solved directly, or we can represent these equation in the matrix form, and then by solving by the determinants we get the values of V1 and V2 in as a complex quantity. Now, we can convert these values in the polar form, as the magnitude is the under root of x square plus y square and the angle is given as tan inverse y by x, or then we can convert these values into the time domain. So, we get our required result. This analysis can also be used for the super node. So, in this figure we have seen that there is a voltage source between the two non-references voltages V1 and V2. So, we will form a super node for this, and then we have to write the two equation. First equation represent the KCL equation for the super node in the phasor form, and second equation gives the relation between the non-references voltage and the given voltage source. Now, solving these two voltages, we can find the voltages V2 and V1, and then we have to find here the current I0, which can be find as dividing the voltage V2 by the resistance 1 ohm. So, and finally, we get our result in the frequency domain. Now, we can convert this result into the time domain and we get our required result. Again, we know that KVL is valid for the phasor. So, we can analyze the AC circuit by mesh analysis also. We will start the mesh analysis by taking a very simple example. In this figure, we have to find the voltage V0 across the 6 ohm resistance, and here we have two voltage sources VG1 and VG2. Again, first of all, we will convert this whole circuit from time domain to the frequency domain. So, first of all, we will represent the voltage sources in the polar or phasor form, and then we will find the inductive and capacitive reactance for the respective given inductance and capacitance by taking the value of omega is equal to 5000. Now, we can consider the two mesh currents I1 and I2, and then we can write the KVL equation for the mesh 1 and mesh 2. Then solving these two equations by the determinants, we get our result for the current I1 and I2 in the phasor form. Now, this current can be converted into the polar form, and then we can get the result our required voltage, that is V0 is equal to I1 minus I2 by multiplying the 6 ohm resistance in the polar form, and finally, we convert it again in the time domain and we get our required result. We can also use the super mesh analysis for the AC circuits as shown in the figure. Here in this circuit, there is a current source is connected between the two meshes. So, we consider a super mesh between the current I1, I2 and I3. Now, writing the KVL equation for mesh 1 super mesh and one another equation which gives the relation between the current I2 and I3 and the given current source. We can solve these equation by determinants or directly, and we get our required result. Now, we come to the superposition theorem. As we have studied earlier the capacitor and inductors, and we know that their response is linear for the AC circuits. So, we can apply this linearity benefit of these elements and we can use the superposition theorems for the AC circuit as it applies to the DC circuit. This theorem becomes very important if the circuit has sources operating at different frequencies. If the voltage source and current source have two different frequency, then we must use the superposition to solve this type of problem. Here we will consider the each source acting alone and solve it by as a separate phasor circuit independently, and then after solving it in the phasor form, we can't add the result. So, we will convert the result into the time domain, and finally, the total response is the sum of time domain responses of all the individual phasor circuits. We can understand this type of problems by taking a very simple problem in which we have three type of sources. One is the voltage source, one is the current AC source, and one is the DC source. Now, in this problem we have to find the voltage across 1 ohm resistance, that is V0, and here we will use the superposition theorem and we will find the V0 as the sum of voltages V1 plus V2 plus V3, where V1 is the voltage due to the 5 volt DC source, V2 is the voltage due to the AC voltage source, and V3 is the voltage due to the AC current source. Here we can see that the frequencies for the AC voltage source and current source are different. Now, by applying the superposition theorem, first of all we will consider only the DC voltage source and setting all other sources to 0. So, shorting the voltage source and open circuit the current source, we get the desired circuit as shown in figure. And now, by using a simple voltage division law, we can find the voltage V1. Next, we will consider only the AC current source and removing all the other sources. So, here now we have to convert the circuit from time domain to the frequency domain. So, the voltage source is given as 10 cos 2 t. So, here omega is 2 t, then we have to find the value of inductive reactance and capacitive reactance for the given inductance and capacitance by taking omega is equal to 2 radian per second. So, we get our desired frequency domain circuit. Now, we can calculate the voltage, phasor voltage V2 by using voltage division law, and then we will convert it into the time domain. In the last, we will consider only the AC current source and setting all other sources to 0. Now, here the frequency is, that is the omega is 5 radian per second. So, again we have to calculate the inductive and capacitive reactance by taking omega is equal to 5 radian per second for the given inductors and capacitors. Then we will find the current flowing from the 1 ohm resistance, that is the current I1 by the current division law, and then multiplying that current by the resistance value 1, we get our desired voltage V3 in the phasor form, and finally we will convert this voltage into the V3, and for getting the result, that is the V0 voltage across 1 ohm resistance, we will add all the individual voltages V1, V2 and V3 in the time domain, and we get our result. As we have seen that Ohm's law can be expressed in terms of impedance in the AC circuits. So, we can use the source transformation theorem by using the Ohm's law, and we can convert a AC voltage source to the current source and vice versa. Here the resistance is replaced by the impedance term. Next, we come to the Thevenin and Norton theorem, which provides us the Thevenin and Norton equivalent circuit for any complicated linear circuit. Both Thevenin and Norton theorems are applied to the AC circuit in the same way as it applied to the DC circuits. The only difference is that the calculated values will be complex. We know that in the Thevenin equivalent circuit, a linear circuit is replaced by a voltage source in series with an impedance, and in the Norton equivalent circuit, a linear circuit is replaced by a current source in parallel with an impedance. Both the two equivalent circuits are related to the source transformation theorem also. Now, for finding the Thevenin equivalent circuit, we have to calculate the open circuit voltage across the terminals, and for finding the Norton equivalent circuit, we have to calculate the short circuit current by shorting the terminals, and the equivalent impedance can be calculated by subtracting all the sources, and the equivalent impedance across the terminal is the required impedance. If a circuit have more than one independent source, then it is necessary for us to determine the open circuit voltage or the short circuit current due to each independent source. Here we can use the superposition theorem also. Let us understand the how we can make the Thevenin equivalent circuit for a given AC circuit in which the reactive elements are connected. Here we have to find the Thevenin equivalent at the terminals A, B. We can see that circuit is already given into the frequency domain. So, there is no requirement of first step, that is the transformation from time domain to the frequency domain. Now, first of all we have to calculate the Thevenin voltage across the terminal AB, that is the open circuit voltage. We can find this voltage by using the voltage division law, and we get our required Thevenin voltage into the polar form. Next, to determine the required Thevenin impedance, we will remove all the sources and made them 0. So, here we short the given voltage source, and now combining the reactive elements in parallel and series, we get the ZTH. Here we can see that the 6 ohm and the inductance are in parallel with the capacitive reactance, and all these are in series with the 10 ohm resistance. So, we get our ZTH into the complex form. Now, we can make the Thevenin equivalent circuit in the phasor form by connecting ZTH with in series with the VTH. In the next example, we have to calculate the current I0 by using the Norton analysis. We have considered the same example in the nodal analysis, in which we use the super node method. So, here we can see this become very easy by using the Norton analysis. So, first of all we will remove the load, that is the 1 ohm resistance, and shorting the terminals, and we will find the short circuit current from these terminal. Here we can see that there are two sources, one is voltage and current source. So, we can use the superposition theorem to find the short circuit current. So, first we will consider only the voltage source. Now, we can see due to the voltage source, the current I1 is the current ISC short circuit current, which can be given as the ratio of voltage source divided by the impedance 1 plus j. Next, we will consider only the current source. Here we can see the whole current will flow from the short circuit. Due to the short circuit, there will be no current from other impedance branches. So, I2 will be the same as the given current source. Now, by using the KCL, we can add these two current I1 plus I2, and we get our required short circuit current into the complex form. Next, we have to determine the impedance Zn or the ZTH at the open load terminals with all sources made to 0. So, we will short the voltage circuit and open the current source, we get our desired circuit as shown in figure B. Here we can see that the inductive impedance and capacitive impedance are in parallel with each other. So, we can calculate our Zn by combining them parallel, and we get its value is 1 ohm. Then we will connect the IN and Zn in parallel and construct our resulting Norton equivalent source, and then we reconnect the 1 ohm resistance across the given terminal. Now, by using the current division law, we can easily find the desired current I0. And we get this value in the complex form or the phasor form, and then we can convert it into the time domain, we get our result in the time domain. In the last, we will consider the maximum power transfer theorem for the AC circuit analysis. Earlier, we have considered the maximum power transfer theorem for the resistive load and for the resistive source, but now we extend our result to the AC circuits. Here we consider the circuit as shown in figure, where an AC circuit is connected to a load and is represented by its Thevenin equivalent. The load is usually a impedance. Thus, for maximum power transfer theorem, the load impedance ZL must be equal to the complex conjugate of the Thevenin impedance ZTH. So, we can state that an independent voltage source in series with an impedance ZTH or an independent current source in parallel with an impedance ZTH delivers a maximum average power to the load impedance ZL, which is the complex conjugate of ZTH. That means ZL should be the complex conjugate of ZTH. To prove this theorem, we assume that ZTH is equal to RTH plus JXTH and ZL is equal to RL plus JXL. Now, we can find the current flowing from the load by equation 1. Then we can find the average output power flowing across the load, that is equal to P is equal to I RMS square RL. Substituting the value of I, we get the average power as written in the equation 2. Now, we know for the maximum power, the differentiation of equation 2 with respect to RL and with respect to XL becomes 0. So, first of all, differentiating the equation 2 with respect to XL and putting it to the 0, we get that XL should be equal to minus XTH. And now, substituting this value into the equation 2 and differentiating again with respect to RL, we get that RL will be equal to RTH. So, we can say ZL is equal to RL plus JXL will be equal to RTH minus JXTH, that is the complex conjugate of ZTH. Now, we can calculate the maximum power transfer to the load by substituting the value of RL is equal to RTH and XL is equal to minus XTH. So, we get our resulting maximum average power is equal to VTH square upon 8 RL. Now, how we can calculate the value of load in a AC circuit for getting the maximum power? We can understand it by taking this example. Here in this example, we have to calculate the value of load for the maximum power. The circuit is already given in the frequency domain, so there is no requirement of transformation. Now, to determine the equivalent resistance, we will make all the sources equal to 0. Here we have one single source, so shorting the source, the ZTH is the equivalent impedance across the given terminal. So, we can find the value of ZTH in the complex form, and then to find the maximum power, we have to calculate the Thevenin voltage across the terminal. So, by using the voltage division law, the voltage across the 100 ohm resistance is the Thevenin voltage. We can calculate it easily. Now, by replacing whole the circuit by the Thevenin equivalent circuit, and for the maximum power, according to the maximum power theorem, the value of load impedance will be equal to the complex conjugate of the Thevenin impedance, that is 100 minus J25. So, load becomes equal to 100 minus J25. Now, we can find the current flowing from this load and we get our maximum power, that is as shown in the calculation. So, in this program, we have learned the various circuit analysis technique applied to the AC circuit analysis. With this, we also learn to transform a time domain circuit into the frequency domain and vice versa. In the last, we calculate the maximum average power transfer for load in an AC circuit. I hope You must have enjoyed this program. Thank you.